Dear students, in the previous lecture, we had seen some introduction to fuzzy logic. So now we will apply that concept of fuzzy logic for our search quality measurement, and we'll call it FSQM, fuzzy search quality measure. So the bottom line is this only. We propose to combine the 7 components of the user feedback vector in such a way that the need of the respective weights is replaced by some appropriate relative fuzzy linguistic quantifier. In fact, I had introduced it briefly on the previous turn itself, that why do we require the fuzzy search quality measure in the first place. So the thing is that how do we choose the weights of the individual 7 components of the feedback vector? That remains a burden on the user. So let us take that burden away from the user and let us try to employ fuzzy logic in order to decide for us how to combine those 7 components using fuzzy linguistic quantifier that we have seen on the previous turn. So you will understand more as we progress during the discussion of this course. So if you see that, if you compare it with the search quality measure block diagram, so this part is constant. We have the user query coming to the search engine preference ordering is coming out, it is being presented before the user feedback, and 7 components of the user feedback vector are being provided by the implicit actions of the user. This ranking goes to Spearman rank order correlation coefficient, and the user preference ordering has to come from somewhere. So this part is different. This part is different. If you remember, in this search quality measure, in this part, we were doing an empirical formula to find out the document importance weight. And then we were doing a descending sort based on that document importance weight. And that was our user preference ordering. But that, as I said, requires the weights of each component and so forth. So what we're doing is we are trying to do away with that requirement using these 3 components. Transformation to fuzzy preference relations. So we will transform each of these 7 components into fuzzy preference relations. And then we will aggregate these fuzzy preference relations using the linguistic quantifier MOST. And then we defuzzify it using quantifier guided dominance degree, and that will give us the user preference ordering. So let us see all these steps by steps. So step 1 of fuzzy search quality measure: convert the preference ordering given by the sequence vector into a fuzzy preference relations RV. We are using this formula. RV ij will be 1 upon 2, 1 plus Vj minus Vi upon n minus 1. So suppose, let us take an example. Suppose there were 7 components, and these 7 components were picked up by the user or clicked by the user in this sequence. That is, document 2 was clicked first, and then document 1 was clicked, and then document 3 was clicked, and then document 6 was clicked, and then document 4, and then document 5. So this is the fuzzy preference relation based on the sequence of clicking. It basically tells you the preference of ith document over jth document. So we can very clearly see that all the diagonal elements are 0.5, 0.5. That means document I will be preferred over document I with a fuzzy preference value 0.5. Document for the same document, obviously it should be 0.5, somewhere in between 0 and 1. Now, if we see I, that is preference of document 1 over document 2. So if we see from the sequence of clicking, 1 is preferred over 2 lesser than 2 being preferred over 1, because 2 was clicked ahead of time. Then, okay, so you feed in this formula and you will find out that this is 0.4, whereas this is 0.6, right? So this is clicked as at sequence 1, okay, and this is clicked at sequence 2. So it will be 1 minus 2 upon 5. Okay, so 1 minus 2 upon 5. 5 because 6 is n is 6. So 1 minus 2 upon 5 will be minus 1 by 5. So 1 minus 1 by 5 will be 4 by 5, right? So it will be 4 by 10, right? So 0.4. In this case, it will just be the opposite. It will be 1 plus 2 minus 1 because this is preferred over this one. So you see ij is vj minus vi, right? What sequence had this been clicked? Let us take another example. 1, 3. So 1 is clicked here and 3 is clicked here. So it will be 3 minus 2 because this is clicked at third position and this is clicked at second position. So 3 minus 2 upon 5. Yes. So it will be 1 plus 1 by 5. It will be 6 by 5. So 6 by 5 in half will be 6 by 10. So 0.6, 0.4, right? Again, if we see 1, 4, see 1, 4 like that. So 1 is here, 4 is here, right? So you substitute the values. If it comes out to be 0.9, it will come out to be 0.1. Similarly, if this is 0.7, it will be 0.3. And if this is 0.8, it will be 0.2, right? So this is how you can have a row and a column. So likewise, using this formula, you will populate this fuzzy preference relation based on just the clicking of documents, right? Just the clicking of documents, it will be preferred. So I've got RV, fuzzy preference relations, given by the sequence vector. This is one component of the feedback vector is taken care of. Let us move on to step 2. Convert the fuzzy utility values given by normalized time vector or normalized cut paste or copy paste vector and all the remaining vectors, namely P, S, B, E, into the corresponding fuzzy preference relations as Rx, where Rx, X may be T, X may be C, X may be P, S, B, E, whatever the case may be. And this is simple, xi square upon xi square plus xj square, where x may be substituted, as I said, by TPS. This way we would have a set of 7 fuzzy preference relations, one each for the 7 components of the user feedback vector. RV, and we'll have RT, RP, RS, RB, RE, or RC. 7 fuzzy preference relations based on individual components of the feedback vector. So as an example for step 2, suppose my T by T max is 0.3, 0.9, which means document 1 was read 30% of the time that would have required for reading it completely. This will document 2 is read 90% of the time, 40% of the time required, 20%, 70%, 50%. So simply by substituting, I can get like 1, 2, I can get 0.3 upon 0.3 square plus 0.9 square. So that will be 0.1, right? So what that will be 1, 2. This is 1, 2. 1, 3 will be 0.3 square upon 0.4 square plus 0.3 square will be 0.36. So likewise, you will populate all the values in RT, and the same way it will all be for S, B, and so on, all the 7 components, right? So now I have got 7 fuzzy preference relations, each corresponding to the individual component of the 7 components of the feedback vector. Now, we all know, we have seen relative fuzzy linguistic quantifier ordered weighted averaging. So now step 3 of first fuzzy search quality measure is the aggregation of individual fuzzy preference relations into a combined fuzzy preference relations. Let us call it RCOM. RC, it might create confusions that it could be copy paste. So let me call it RCOM. And we can make use of most. What does it mean? I have 7 matrices, right? One for V, one for T, one for P, and so on. So I have to combine R11 of all of them. I have to combine R12 of all of them. So I can make use of the fuzzy quantifier most. See, now that weight in the empirical formula is done away with. I'm simply saying most, and whatever is available, the same will be included. So I've written it RCIJ is equal to k is equal to 1 to 7, wkzk, where zk is the kth largest element in the collection, rvij, rtij, rpij, rs, the ijth value of the fuzzy preference relations corresponding to any one of the components of the 7 feedback factor. So Wk is the kth value of the weight vector corresponding to the relative fuzzy linguistic quantifier most with the pair A is equal to 0.3, B is equal to 0.8. All this we have discussed in the previous term. So this implies that we wish to combine most of the metrics from amongst B, T, P, S, B, E, C. So 7 different fuzzy preference relations, which are square matrices to a single square matrix RCOM, which is a combination of all the 7 components of the feedback vector and tells me about the preference relation of the ith document over jth document when all the 7 components are taken into account. So example of step 3, let us assume we are talking about 5 2th value of RV, 5 2th value of RT, 5 2th value of RP, and so on, 5 2th value of RC. The relative fuzzy linguistic quantifier most with the pair 0.3, 0.8 gives W1, W2. We've already found out and we know how to find it out. So now RCOM 5.2, it should be RCOM, different from this RC. This is RCOM, right? 5.2 will be W1, W2, W3, all these 7 weights into the descending sort of RV 5.2, RT 5.2, RP 5.2 transpose. So it will be like this, R and multiplied by the column matrix or the vector based on these 7 components. So it will be, we have already seen it, it will be W1 into the largest of them, so which is 1, W2 into second largest, W3 into third largest, W4 into fourth largest, W5 into fifth largest, W6 into sixth largest, and W7 into seventh largest from amongst RV, RT, RP, RS, RB, RE, RC, all 5 tools. So this will give me RCOM 5.2. So that way I can have a complete combined fuzzy preference relation matrix. So now my next step is to defuzzify. Step 4, convert combined fuzzy preference relations RC into the combined utility function ordering YC using the quantifier guided dominance degree. So this is again OWA processing, but we will change the linguistic quantifier to as many as possible now. So what we will do, we have RC like this. Okay. So what does this row indicate? This row indicates the preference of document 1 over document 2, preference of document 1 over document 3, of document 1 over document 4, and so on. Document 1 preference value over nth document. So now I have to find out one value, which is the absolute value of preferring this document over the remaining documents, right? Over all the remaining documents. So this way I'll find out this value, I'll find out this value. So now when I do the descending sort on this, this will give me the combined preference of documents, right? So let us see. In order to reduce this row into a single component, I'm making as many as possible. As many as possible documents over which document 1 is preferred. As many as possible documents over which document 2 is preferred. So this implies that we wish to combine as many as possible of the elements of the ith row of RCIJ to get a quantification of the dominance that the ith document has over all others in a fuzzy majority sense. Okay, so it should not be RCIJ, ith row of RC. So I'll strike it off. Combined fuzzy preference relation, ith row. Okay, so let us take an example, it will be clear. For the fuzzy quantifier, as many as possible with the pair A is equal to 0.5, B is equal to 1, the corresponding Lovo operator 1 by 3, 1 by 3, 1 by 3. Okay, so RC4J, suppose RC4J is 0.332, 0.228, 0.260. So this is the row, the fourth row of the combined fuzzy preference relation. So now YC4 will be this W into the descending sort transpose of RC4J. So it will be 0 into the largest of them, which is 0.603, plus 0 into second largest, which is 0.598, plus 0 into third largest, which is 0.5, right? And then 1 by 3, which is 0.33 into fourth largest, which is 0.332, and 1 by 3 again into fifth largest, which is 0.260, and 1 by 3, which is 0.33 into the smallest, which is 0.228. So I get 0.273. So the entire row is reduced to a single value. Similarly, this entire row will be reduced to a single value. This row will be reduced to a single value, and the last row this way will be reduced to a single value, right? So step 5, sort the elements of YC in a descending order. This gives the combined preference ordering OC. For YC that we have found out like this, sorting in the descending order would give me the descending order means the largest first. So you see 0.517, 2 is preferred. And then second largest from amongst them is 0.464. So 3, right? 2, 3. And third largest from amongst them is 0.437, right? So it is 1. And then fifth largest is 0.286, which is 4. And then 0.273. So sorry, this is fifth, this is fourth, and this is sixth. So this is the combined preference ordering after having taken into account all the 7 components without bothering about the weights. The weights were calculated, in fact, by the OWA, ordered weighted averaging. So the user doesn't have to worry about the weights. The ordered weighted averaging will take care of the weights, right? So this may be taken as the user preference ordering, which will be compared against the search engine ordering using Spearman rank order correlation coefficient. So if I take you quickly back to the block diagram, yes, this block diagram, see 7 components, we converted each of those components into a fuzzy preference relations, then we combined all of them, all the 7 fuzzy preference relations into a combined fuzzy preference relations, and then we did the defuzzification, we sorted it, and the user preference ordering we could get, right? And they are compared, and fuzzy search quality measure is found out this way. Okay. So let me get back. Yeah. Similar to the procedure of SQM, the combined preference ordering OC is compared with row, the sequence in which the documents were initially shortlisted by the search engine or initially listed by the search engine. The Spearman rank order correlation coefficient is found between OC and row now, right? We repeat this procedure for a representative set of queries and take the average of RS. The resulting average value of RS, which could be average or wind whatever, is the required fuzzy measure of the search quality, FSQM, right? So these are the results, performance of search engines based on the 3 components. We just taken 3 components. So correspondingly, you will generate just 3 weights. So the same result, but found out in a different way. And when you took the sequence of untouched documents average, it gets more onto the positive side. So this is about the Yahoo preference, Yahoo search engine followed by Lycos. So you can see that I've compared SQM and FSQM. So there may be some difference between their absolute values, but their relative ranking remains the same. SQM, FSQM, their relative ranking remains the same. So which means FSQM retains the performance by the search quality measure, but in a more convenient way. You don't have to put the weights. The ordered weighted averaging will put the weights for you. And so the burden is taken off the shoulder of the user, right? So let me, yeah. So now let me move on to the topic web coverage. The underlying principle is to collect a uniform sample of the web pages. The belief is that more the web coverage of a search engine, better the search engine would perform. So how can we find out a uniform sample of the web pages? By carrying out random walks on the web. This uniform sample is the size of the search engine. This index size is an indirect means to estimate the performance of the search engine. This is the point I was trying to make. This index size is an indirect means to estimate the performance of a search engine. Larger the index size, more is the web coverage and more likely is the emergence of good search results. So what can we do? We can do a random walk on the web and pick up a few samples. Now, what is the percentage of those pages that we have picked up through the random walk, which is indexed by the search engine? Suppose I did 10 random walk steps. So I picked up 10 pages, 1, 2, 3, using random walk, right? Random walk is a very standard technique, right? Now, suppose I went to a search engine. I went to a search engine 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this search engine has covered 40% of these random walked samples. So which means I can generalize that our search engine has 40% coverage. Another search engine comes in and it shows 60% of these pages covered. So we can do that. The coverage is 60% for that search engine, and hence that search engine may perform better because it has got a wider web coverage. So this random walk on the web is a very useful technique. Using this technique, you can estimate how many of the web pages are .org pages, how many of these pages are having an average size above certain limit like 1K or so, how many of these web pages are .edu pages. So that way web characterization you can do using random walks on the web. By random walk means picking up some random samples and assuming that these random samples are representative of the entire web picture. Because to cover the whole web is not easy. Web coverage of the entire web may not be easy. So you do random walk. Okay. And then you make a lot of inference from there. So web characterization, how do the public search engines compare? What is their web coverage in terms of their index size? Broader questions may include how many web pages are there in all, what is the percentage of .com pages, what is the average size of the web pages, and many more. So once we are able to do the random walk, we can do a lot of web characterization exercise, like a few of them which I have listed here. To answer these questions with precise answers is not easy. So we provide estimated answers, but obviously this estimation should have proper statistical backing. Otherwise, anybody can say anything. But once you are doing it using random walks, then it is supported by strong theory. For that, we need a uniform sample of the web. Researchers have done random walk on the web to get the uniform sample. One of the ways could be using PageRank. We estimate the quality of indices by random walks. This is the work done by Hensinger in 1999. What we do, they start with a seed page. Now, out of these seed pages, there may be several links. So you branch to any of the pages of these random links based on the PageRank value as the probability of clicking, right? So you click any of those links by having the random number generator and then finding out which link is to be clicked. So for example, the random theory says that I have to click this page, this link, right? So you branch to another page. So this is first sample, the seed sample. Now this becomes the first sample. Let me call it 0th sample and then first sample. It will have several links. So you click any of them randomly based on the PageRank value of the links that they point to. So you go to another page. So this will be your second sample and so on. So suppose each page P of the web is given a weight WP. We define the quality of the index as the entire index as summation of all the pages that are indexed by it, of the index values of the pages that have been randomly sampled or that have been landed through random walk. Since W is a scale, we always have WS between 0 and 1, right? So measuring index quality, page rank taken as a weight function, surfer visits page P, random walk in state P. Pages with high page rank are more likely to be visited than pages with low page rank. All this we have discussed when we were discussing the page rank, right? That page rank may be taken as a way for doing the web traversal, focused web crawling. If you remember, we talked about focused web crawling there. So we can approximate the quality of a search engine index S according to the weight W by independently selecting pages P1, P2, Pn and testing whether each page is in the index S or not. Okay, like here we have done for a few pages, 1, 2, 3, and then we see how many of the pages that we have randomly sampled are there in the index. So that will be the quality of the index of the web page, right? So measuring index quality, let I if we are and 0 otherwise. Our estimate for WS is 1 upon n. We take the average of all such i's. So we merely need to measure the fraction of pages in our sample sequence that are in the index S in order to approximate the quality of S, right? The point that I've been emphasizing time and again, how many of the randomly sampled pages are there in the index? So that if 100% of the randomly sampled pages are there in the index is 100%. If 60% of the sampled pages are there, the index value is 60%, or index performance is 60%. The quality of index is 60%. To remove the bias toward pages walk based on the inverse of an estimate for the page rank of each page. Page rank of a page P is made to be the visit ratio. That is the fraction of number of times the page P was visited during the walk to the length of the walk. The length of the walk is how many it has been sampled, and page rank may be taken as how many times a particular page has been landed using the random walk. So graph random walk for the web. Random walk on a graph requires that the graph must be connected, undirected and regular. The natural graph model of the web does not satisfy, because we all know that it is directed. For our case, it may not be connected at many points. It may not be regular even. So assuming that the random walk can follow the links either forward or backward so as to make the web graph appear undirected. So we can take both ways and assume that it is undirected. The non-indexable and inaccessible portion of the web is out of bound for our study. The remaining accessible web is connected. This is called dark web, which is unaccessible. There may be a huge portion of the web which doesn't have any input link from anywhere. So this is called dark web. Nobody can land into this unless somebody originates from there itself. To make the web graph regular, each web page is carrying number of self loops so as to equal of each page. We assume those many self loops. Otherwise, we don't assume self loops. We discard self loops. Do you remember why? Because self loop means keyword spamming. The problem will come back. In page rank, we are dependent on how others are telling about me, not what I am telling about myself. But in order to make the graph regular, we can have a controlled number of self loops. So web graph is now suitable for the random walk algorithm meant for a graph. So I can conclude that using graph random walk, we can have the entire characterization of the web and hence the quality of the index of a search engine. Then Bharat in 1998 came up with some random queries. And these, instead of random walks, they came up with random queries. Random queries generated from a lexicon of about 400,000 words, 4 lakh words, built from a broad crawl of 3 lakh documents in the Yahoo hierarchy. Authors admit this is subjected to biases. Longer pages are more likely to be selected by the query approach than the short ones, because these random queries are very important for studying the web. If the queries are not purely random, then we have got biases. So that is why they are saying that longer pages may have biases because more keywords will be borrowed from longer pages. So Lawrence 1998, they came up with a standard query log like that of NEC Research Institute. But this leaves questions as to the statistical appropriateness and the repeatability of the test, because this is just a query log. How sound is this query log as far as random theory goes? That is not established. In 1999, however, they based on random generation of IP addresses. You all know IP addresses is the 32-bit, or if you talk about IPv6, it is 128-bit. So you generate random IP addresses and you try to see whether those pages are available in the index or not. Obviously, it has genuine doubt about the scalability when we are talking about 128-bit IP addresses in IPv6. So these are some of the approaches that people have done for carrying out the web characterization, and hence the quality of the index of the search engine, web coverage, and hence the quality of the search engine. Hawking 1999, they made a test data set for evaluation of web search systems and techniques by freezing a 18.5 million page snapshot of a part of the web. Using this data, it has been concluded that the standard of document ranking produced by public web search engines is by no means state of the art. Obviously, in 1999, it was not state of the art, but whenever you freeze such a thing, obviously web is very dynamic, so it changes fast. So that study may be pertaining to 1999 only. After that, you need to have a new freeze. Then people came up with ad hoc queries for two different sets of ad hoc queries. Lee in 2000, they took the results from AltaVista, Google, and InfoSeek, evaluated using vector space model. You know about it already. Agree with the manual evaluation of relevance based on precision. So precision scores are given as 0, 1, or 2, but this is similar to form filling. We are asking the user to fill whether it is relevant by factor 0 or by factor 1 or by factor 2. So obviously this will be non-scalable. Traditional IR techniques are there for precision evaluation. Moreover, 3 levels 0, 1, 2 scoring to mimic manual evaluation. 1726 and 1383 queries from IEEE Transactions and Knowledge in Data Engineering, which is a very high quality journal, and PDS respectively on 6 search engines. Google came out best. This was in 2002. Northern Light and IWAN second default, and exact phrase search modes respectively. Okay, so we will stop here. We have seen many techniques. So we will stop here and we'll continue from here on the next turn. Thank you very much.